Today's lesson's on section 10.1, graphing y equals ax squared plus c. It's our first step into graphing quadratic equations. As I've got on the board, I've got a couple linear equations up here I want to talk about first. Because as we have talked about in class plenty of times, even when we're learning some of these new families of functions, it's still best to relate it back to something that we know and understand very well. And linears, we've worked with tons of times, right? We've got hundreds of linear equations in the past couple of years as we've been learning how those type of equations function. Linear equations, again, a reminder, always means straight line function. We're getting into curved graphs now, but there are still some things we can take from what we learned about linears. First thing I want to talk about is how did we first graph a linear equation? What did we start off by doing? Because that's typically when you start learning about a new family of function, a new type of function, like a quadratic. Again, like we're doing right now, quadratic means that I have x as my independent variable and it's squared, and that's the highest power. That's the degree of this equation, a degree of this polynomial. Well, since it's squared, it's going to do something a little different. But think about how we first learned how to graph a linear. Y equals something like 2x minus 3. And some of you may even think, well, remember one of the first things we started to do was slope-intercept form, right? And say that the slope is 2 and the y-intercept is -3. We could make a graph from there. But really, that's not even the first way you probably learned how to graph even a linear equation. Before that, you did learn that too. And that was maybe like a little quicker way. And that's something we'll talk about too, to understand how the numbers in the equation affect what the equation, what the graph's going to look like. But the first thing you probably did to start looking for patterns, to start understanding how these graph, was by making an XY table and finding some ordered pairs, some solutions to this equation, an X and Y value that work, and then plotting that on the graph. And those are our ordered pairs, our points, our solutions that start making the graph of our line. So for example, let's say again, this is our equation. We're going to start graphing. This is probably the first way you started to learn how to graph. For a linear, maybe you plug in some numbers. I'm going to pick some negative and some positive. -2, -1, 0, 1, 2. Some numbers like this. And I substitute those numbers in and I see what I get for y values to make a solution to this equation, x and y combination that work. -2 times -2 give me -4. And then -3 would give me -7. Putting in, substituting -1, and -1 times 2 gives me -2, -3 gives me -5. If I put in 0, kind of a nice one, 0 times anything gives me 0, -3 gives me -3. 1 times 2 gives me 2, -3 gives me -1. And 2 times 2 is 4, -3 gives me +1. And then these are all ordered pairs. I plot on the graph and show me what the graph of my line looks like for this linear. So -2, -7, 3, 4, 5, 6, 7 will be right down here. -1, -5, 0, 3, 1, -1, 2, 1. And you'd graph a linear something like this. And from there, you start to see the patterns and what the graph would look like and what it does. And how does the slope relate to what I see on the graph? Well, it ends up being the measure of steepness, right? The bigger this number is, as we'll talk about with quadratics too, the bigger this number is, what do you know, the steeper the slope ended up being. And even the -3, right? That had a relationship in terms of how it showed up on a graph. The -3 was like the y-intercept, the place where the line crossed the y-axis. These numbers, understanding how these work, can still and will still help us understand how quadratics work as well. There'll be some of the same relationships. Some things different, of course, but still understanding how slope and y-intercept and how the points, the patterns that we saw in these ordered pairs, what happens with the numbers as I plug in x values and y values, starting to see those in these first couple days of graphing, we will be making tables like this so we can start seeing some patterns. What is showing up? What's happening as I continue to go up and up for my ordered pairs and increase x by 1? What's happening to y? What are the patterns that I notice in quadratics and how are they different? So taking that same approach now to a quadratic equation. So we're going to graph. I didn't finish all the ones on that first table or that first page. Just wanted to give you one example again what we see with linears, and we have other ones on there, but again, that was just to give you an idea of what we first did with linear equations. Now let's try that for our first quadratic. Y equals x squared. What's going to happen? Well, again, we're going to talk about all the ways that we're going to use to graph these kind of equations as well, but the very first way we're going to learn And the way we'll do it today in the homework, and then any time in this first section 10.1, how we'll do in the homework is by making an XY table. I still think just like we did on the first page for our linear, you're going to find it helps me put in a few negatives and positives when we can. We'll talk about in the future way maybe that's not really possible, or we can pick some better numbers. But in this case, today, we'll find out -2, -1, 0, 1, 2. It's kind of a nice set to start with, and you'll see why as well. We'll start seeing some patterns for things that happen, and I want you to see these using the table as well. Here's how quadratics act. So start off by putting in some of these numbers. I'm actually going to start with 0, the very one right in the middle here to get us going. And if I put in 0 for x, 0 squared just gives me 0, so that's kind of a nice starting point. Okay. Then I'm going to go to my other positive number 1. Well, 1 squared just gives me 1, so 1, 1 is a point. Okay. And 2 squared is 4. Now, we're going to find this in quadratics. Maybe you're starting to see something already. As if you feel the rest of the table going ahead of me, that's totally okay. But what happens now when I put in some of these numbers like -1 and -2? Well, remember, when I square a negative number, it actually turns it positive. -1 times -1 just gives me +1. And -2 times -2 gives me +4. In quadratics, because we end up squaring things, we see patterns like this sometimes. Notice what I've got on the right side. Again, you have to find out where that is in terms of what numbers of x we have to plug in to get this pattern, but this is always going to happen, and we'll see what happens with on the graph. But notice I've got 0 here, and then I get some of the same numbers on each side, 1 and 1, and 4 and 4. Think about what that's going to look on the graph right now before you even start graphing. But putting these points in, let's try it though. Again, hopefully you have some kind of mental picture. What should you expect to happen? But take a look at the points. What's it going to look like? Well, plot my first one, 0, 0. And then I'll do my positive ones, 1, 1, and 2, 4. And then my other ones that I put in, -1, 1, and -2, 4. And notice I start getting almost like this. It looks like maybe a V, but we're going to find out parabolas. Quadratic equations have a U shape, so you're going to try to make it as well curved as you can when you're making a graph of these quadratics. I'm going to add one more point to the table just to emphasize the point. I haven't drawn the line yet, but I'm going to add one more point as well. What if I put 3 in for x? Well, 3 squared is 9, correct? So I bet you can tell me also if I kind of squeak it in the top here, -3. What's a -3 squared? Also gives me +9. So just to give myself even a little more definition for this, always put in a lot of points to give yourself a good idea what the shape should be. But 3, 9. And -3, 9. When I draw this graph, it should look like some kind of nice smooth curve, some kind of U shape. Do the best you can, especially the first couple of days that we're graphing. I don't expect it to be perfect, but there's what a quadratic graph always starts to look like, this U shape. And scrolling down to the bottom of the slide, that's exactly what I have you right here. What you're going to find as we're doing graphing quadratic equations, whether we change a lot of the numbers around or whatever they may be inside the equation, whenever we have something that's degree 2, we're going to get this shape that we call a parabola. A parabola shape. And just note that a parabola can be a U shape. We're also going to find, you can think about it too, how can I get can also be an upside down U shape as well, but that's what the graph of parabolas at degree 2 equations always look like. That's a quadratic graph. Another thing I want you to jot down is kind of an important point in a parabola. We'll think about linears where always just straight line, positive or negative slopes. They're always increasing or always decreasing. There was never this, if you go back to our graph, right? There was never this kind of point where the graph turns around. A parabola always has this point, that one distinct spot on the graph where, okay, before it was going down, 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 it's getting slower, slower, slower. Now all of a sudden it gets to this point where now it's going to start turning back around and going up. There is always this distinct point, which is in quadratics, in problems, in word problems, things like that, always is kind of an important point for us. We call that the vertex of the parabola. We call it either highest. It can either be the highest point on a parabola, or it can be the lowest point on a parabola. And you can see that by the 2 U's that I have here. Taking a look right here, the U shape. If it's like a normal regular upside down U, there's some kind of lowest point in the parabola. I know that's kind of small to see, but there it is. Or if it's the upside down U, And there's some highest point on the parabola where the parabola increases all the way to a certain point and then starts falling down. Well, the vertex is that highest or lowest point on the parabola. And in our table, sometimes we can find it. Taking a look at our table up here, okay, I bet you we can see on our graph, and you can kind of see from the table, right? We went from going from top to bottom, 9, 4, 1, 0, 1, 4, 9. Right here, our vertex, labeled with a V, is 0, 0 for this particular graph. For the 3 problems below, I want you to make the tables. Right now, it's kind of examples for what things we would graph. I think today on the homework we'll be making the tables as well. This first day, we'll learn in the future how there's some other kind of quick hand ways we can draw them, but this first day, we're going to make tables for each of the equations and then start to make a graph for it as best we can. And I want you to find the vertex in those particular tables as well. And you'll notice something today on the ones that we're working with. And then in the future, we'll talk about what happens. We'll get a little different answers, but make a table for each of these and then find the vertex. I will start kind of going through this slowly up here as well, too. Go ahead of me again as you wish. I'd say for today, good numbers to plug in just like we did for those first couple. -1, -2, -1, 0, 1, and 2, I think are good starting points. And as you know, it's for a pattern that kind of works today. You can start anywhere, but it's kind of nice to put in 0 first. Since 0 will give me -5. And then maybe do the positive ones, and then maybe we'll even notice a pattern. We'll double check it, but we'll notice a pattern going the other way too for a lot of the graphs that we do today. It won't always work, but today, a lot of times it will. 1 squared gives me 1, -5 gives me -4. So if I put in 1, I get -4. If I put in 2, 2 squared gives me 4, -5 gives me -1. Putting in -1, -1 squared still gives me +1. -5 still gives me -4. What do you know? So I bet I'm going to get -1 for that one as well. Looking at that table, again, I can see the pattern. Going from -1 to -4 down to -5, and then it starts going back up again. So right here, kind of an important point, right? Looks like for this particular table, 0, -5 is the vertex. And we'd look at the graph to kind of confirm that, but knowing the pattern we're going to use today, and the first ones we're working with, yep, that's the vertex of our table. If you need to pause the video right now to do the other 2 tables, go ahead. I'm going to also just put these in. I'm going to pause the video myself, write these in, and then show you what the answers are. So if you need to pause and make sure you get them done first before I get them done, go ahead right now. So here are the tables for the other 2 equations we got up there. And you might again notice a pattern right now. This won't always be the cases we're going to find, but in the ones we're doing today, notice that my vertexes end up being that middle point, 0, 0. And in this case, 0, -5. I see those patterns, and we'll start looking at some patterns more with the numbers too and what they are doing. But there's that lowest point in my vertex, and we'll talk about when it's the highest point too. Today happens to be the middle point. It won't always be that way. But maybe just from these first couple tables, you can see kind of how that works, and just notice especially the symmetry we're seeing. -3, -3, and 3 and 3. As I plug in numbers, we'll still always see that, even with different numbers or different x values in the table. But we'll see this pattern, something going down and coming back up, or even going up and coming back down. Now, today when we're graphing, and when we're in this section 10.1 graphing, we're going to use tables and kind of find ordered pairs and look to see some of the patterns there. But I also want to talk about qualitatively. Here's what, as we move on in this section, I want you to start to understand and realize as you're graphing these different equations. We talked about how we can relate quadratic equations still to linear equations and how they have some of the same relationships in terms of what the numbers do and how it affects the graph. Take a look on the left side. I've got some linear equations, and we talked about in the past the linear parent function. Right? The most basic linear function, the one that all the ones are based off of, just y equals x. It has a slope of 1, and it's a proportional relationship, means it goes to the origins. Take a look. Notice down here, the black line is the linear parent function, right? Crosses the origin and has a slope of up 1 and right 1 continually, okay? I've done that for the parent quadratic function as well, because we're going to talk about what happens when I start adding numbers to this equation. So notice I've already got that down there, and you can put that on the next 4 graphs as well in the next couple slides. I know it's got the different quadratic equations on there, but you can put the parent function. It's just the one that we graphed on one of the previous slides there, where it's y equals x squared, and I think we had these as points in there, right? -2, -1, 0, 1, 2. And it's just where each of these numbers gets squared. So 0, 4, -1, or -2, sorry, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. It's just where I take the x value and square it. So there's what that graph is, the parent quadratic function. And we're going to talk about what happens when I start adding numbers to this function. What happens? Well, similar things that you noticed for linears, similar type of characteristics. That's why we're going to compare it to it. And we'll see if we can start to figure them out even before I do it right now. Take a look at some of the linear examples. And I'm going to talk about what the quadratic ones do, but see if you can even figure out what's going to happen to the quadratic equation, the graph, when I start putting some numbers to it. So for example, take a look at linear equations. Again, the black line here, this first graph, the black line is the parent function. And then I've also graphed this equation right here, y equals 2x. Well, notice, what's the difference in these equations, right? My slope is 2 now, as opposed to 1 like the parent function. The slope is 2. And what did we learn about slopes? As we make slope a bigger number for a linear function, what happens to the graph? The line gets steeper. Slope is a measure of steepness. And the line will, if I have a bigger number for the slope, the line will also get steeper. And see how now it's rising more quickly from left to right. Well, guess what? For quadratics, something similar kind of happens. This number isn't exactly the slope per se, but it does tell us kind of how steep our u is going to be. If I have a number like 2x squared, and I put numbers in the table, and we're going to find, again, I'm not going to use the table right now, but just kind of showing you qualitatively what you should expect to happen is I'm going to get a steeper u as well. Now in this case, it's not going up or down, like it's just a U shape, so both my lines are going to go up in my U shape, but it's going to get skinnier almost. I can think, and it's almost like I'd like to think instead it's getting steeper is probably a better way to describe it. My U is getting just like all the points on a linear function, all the y values are increased from the parent function. They're all going up from what the normal function is, the parent function. Same thing here, all the y values are increasing, going up, so it's making this, as we're going to find out, this is called a stretch. It's stretching all the points vertically. And so I'm going to call this a vertical stretch. All the points that were on our original parent function get stretched vertically, stretched higher, and it makes the u seem skinnier, or again, all the points on it are higher, so it makes it steeper, just like a slope does. And a bigger number, guess what? A bigger number for the number, that 2x squared, or in case it's 2x squared, or 4x squared, or 6x squared, as that number gets bigger, what do you know? It's going to stretch that u even more and more, and make it appear even steeper and steeper. So then going down to our next example, take a look at the next linear and see if you can take a crazy guess at what do you think is going to happen. Remember, for linears, if I had a slope that was getting smaller, less than 1, between 0 and 1, right? Now all of a sudden I have a flatter graph, a flatter linear line than the parent function, because I've got some kind of, again, it could be a fraction, but more importantly, what it has to be is between 0 and 1. It could be a decimal too. So between 0 and 1 made like a flatter graph for my line. Well then, if you had to take a crazy guess, what do you think is going to happen if this same thing happens in a quadratic? Well, just like it does here, it's almost like the U shape is going to get flatter. And so it's going to almost look like it gets wider, really. That's what's going to happen. It's bringing all the coordinates for the parent function down. And so my U shape, as we're going to find out, I'm not making a table right now, but the graph of this problem is almost going to look wider. And what it's called a vertical shrink, because it's taking all the y coordinates of the parent and shrinking them closer down towards the x-axis here. So this is called a vertical shrink. If you want something else to write with it, it's when that a value is going to be between 0 and 1. Just like we saw with linear slopes as well. When a is between 0 and 1, funny things happen to different families of functions. You're always going to find that. This is when we see a vertical shrink. Again, kind of looks like the U-shape is going to get wider and shrink closer to the x-axis. Going back to vertical stretch for a second, I should put something with that too. This is when a is greater than 1, right? Just like with a slope. When the slope is greater than 1, we got a steeper line. Same thing here. Again, kind of like the slope for a linear, but for a quadratic now. Anything bigger one makes it steeper. Anything between 0 and 1 makes it flatter. For our last two slides, again, same type of thing. Try to go ahead of me if you want and pause the video, see if you can figure out what do you think is going to happen for these two functions compared to our linear functions. Y equals negative x. Remember, if I had a negative for a slope, what it really did was take a look at our graph. It was really like a reflection. That's what happens. Reflection over the x-axis of the graph. Now my slope is going down and to the right. And it's still negative 1, but down to the right compared to the positive slope for a parent function up and to the right. Well, what do you know for quadratics? We're going to see something kind of similar. First of all, there's our parent function on there now. But when I have y equals negative x squared, it's going to also make a reflection, my u shape. And we'll see this from the table. All my points, my y-coordinate is going to be negative now. I'm going to still put things in and square them, but then make them negative. And so what's going to happen is on my graph, I'm going to get that downward shape in u, downward face in u, the downward parabola. That's what a negative will do for my graph. So I can say when a is negative, we get this graph, which is a reflection. And our last example here of a linear relating to a quadratic, y equals x plus 3. What would happen compared to the parent function if all of a sudden I start adding a constant or subtracting something for a linear? Well, that would just be a translation, right? It just moves the graph up or down. So this is parallel to the parent function, my new graph here, but it's just slid up 3 spots from where the parent function was. So same kind of thing for a quadratic. And let me get my parent function graph here. There we go. So compared to the parent function, this is really going to be the exact same graph, just slid up 3 spots from before. It's really going to be all the same points and things that we used for the parent. But everything is just, all y-coordinates are up 3. So it looks exactly like it. But even the vertex, even that lowest point, is just slid up 3 spots from it. Guess what? If it was x squared minus something, it'd be down that many spots from it. So this is just a, as we've called it in the past, a translation. And it's just when C is anything but 0. Then we know the graph is going to move up or down some direction, some amount.